Well, it's a great honor and an immense pleasure for me to give this talk today at LNS 46, and thus to be able to recall those marvelous 4 years that I have spent at the Center for Theoretical Physics between 68 and 72. I must say that both my wife and I still remember those years as some of the very best, perhaps the very best of our life. And of course, we can say that that was youth or the birth of our first child here, the discovery of such a great country. But it's also the fact that we came back to Europe and to Israel with the feeling of having enriched ourselves and to have made so many nice friends whom I really thank very much today. In fact, I would like to conclude this by thanking most of all the person who sort of twisted my arm and brought me here and with whom I had a beautiful collaboration. This is Nambu Fubini, who will arrive today to join us in the celebration. The subject of my talk, let's see, I think I need to, oh yeah, there it is. The subject of my talk is from dual models to strings, right? Okay, that subject will be covered in this first 5 points. And then I hope to have some time to tell you about how things have developed since that period. I arrived at MIT in the beginning of September 68, but a few months earlier, in the summer of 68, I had worked at what became known as the Dewar resonance model, and I want to start my story from there. Now, I get often upset when reading accounts of early days of string theory. You hear Veneziano has just opened Bateman and found the beta function sitting there, and that was the start of string theory. Now, I think this is an important lesson. This was a rather long-lived model. As you will see, it died and resurrected again. And I guess the reason for that is that it was some good blending of phenomenology and of theory. So let me go over the main phenomenological inputs of the Dewar resonance models and then the theoretical ones. In those days, people working on hadronic interactions knew that the spectrum of hadronic state was extremely rich. Many, many resonances were being discovered almost daily or weekly. Now, those resonances were found to lie on almost straight Regge trajectories, on which I will say more in a moment. And then another property that Dollenhorn and Schmidt found is that the resonance description of a strong interaction collision was complementary, we would say duality, to another description given in terms of the cross-channel exchange of Regge poles. Finally, the quantum numbers of the resonances which were being discovered were all consistently non-exotic. By this meaning that their quantum numbers could be described in terms of QQ bar or 3-quark systems. Now, to those phenomenological inputs, we try to add some good theory, I hope. One was to impose causality in terms of good analytic properties of scattering amplitudes. The second property was exact crossing symmetry. And finally, we took the perhaps bold idea to work in a narrow resonance approximation, an approximation in which resonances have zero width, don't decay, and therefore the scattering amplitude, instead of being described in terms of Bright-Wigner, is described in terms of simple poles. So that was the beginning of the dual resonance model. And as I arrived at MIT, Sergio Fubini and I started immediately to look into more properties of those models. And the first thing to do for us was clear. It was to count the states. In other words, what physics was lying behind those poles in the scattering amplitude of these models. And, well, first of all, we knew that the poles or were equally spaced in the squared mass. In other words, the mass of the resonances were given by this very simple formula where capital N is an integer and alpha prime and alpha 0 were two constants to be fitted to the data. Or pictorially, you could plot the angular momentum and the square mass of your states, and they were all lying on straight line trajectories. These are the Regge trajectories. But still the question was, how many states were there at level n? And the answer to this question could be answered in principle easily. In practice was a different story, by using a fundamental property of resonances known as factorization. By looking at the amplitude for any initial channel to produce any final channel near the pole, we could try to write it in terms of the product of the coupling of the initial state to some resonance times the coupling of the same resonance to the final state times the resonance propagator, which was just the pole. And if you could succeed to represent indeed for every initial and final state that amplitude in terms of a finite sum of factorizable contributions like that, then the number of terms that that sum contained was nothing but the level degeneracy. Now, of course, knowing that the resonances had higher and higher angular momentum gave us already some hint that there had to be degeneracy. For instance, the most naive expectation would be that the degeneracy would be 2n plus 1, 2j plus 1, or probably higher because we knew there were also states of lower spin lying down. But the answer we got by the explicit check of factorization was absolutely surprising. So what we and Bardacci and Mandelstam got was that the degeneracy was growing enormously, like an exponential of the square root of n, therefore recalling this formula as an exponential of the mass at large n. Okay, that made quite a bit of sense. In fact, it agreed with some model put forward by Hagedorn much earlier to explain some spectra of secondary pions in hadronic collision. Of course, this maximal temperature later on was reinterpreted in QCD as the phase transition to the quark-gluon plasma, but that's much later. And that formula was also that exponential spectrum, and the concept of the maximal temperature was also applied by Kerson, Wang, and Steve Weinberg in those days to the early universe. Now, so the first discovery was this extreme richness of the spectrum of the dual resonance model. And what came next was that this very rich spectrum could be represented in a very simple way, which goes as follows. It's quite simple. You take a Fock vacuum, call it 0, and you act on it with harmonic oscillator type creation operators. So you introduce the usual AA daggers of the harmonic oscillators, except you introduce them in several species. Each harmonic oscillator has a Lorentz index mu, going from 0, 1, and 3, and another integer n. which just takes over the natural numbers. And you impose some sort of standard commutation relations between creation and destruction operators with a little catch that you have to put a funny minus sign when the commutators concern the time-like components. And that was simply by Lorentz invariance. Then a generic state which could achieve that factorization was simply the general state that you could get by applying repeatedly creation operators on the vacuum. So they were labeled by just occupation numbers, the usual thing. And the mass formula for such a state was given by this operator. The mass square operator was just the occupation number, except that they were weighted by this integer n. That explains immediately the huge degeneracy as coming from the fact that you have infinitely many oscillators, n, m goes to infinity, and that the frequencies of the oscillators are all multiple of a fundamental frequency. That's this n sitting there. Now, that already smells of a string. We know that a string has many vibration modes, and they are multiple of a fundamental frequency. And Holger Nielsen, Lenny Suska, and many others said, but that must be a string. But that was not coming yet. Let me rather go back to this problem with relativistic invariance. The relativistic invariance of the theory implied, as I said, that the time-like oscillators A dagger 0 n were giving states of negative norm when acting on the vacuum because of this minus sign in the commutator. This negative norm state violated probability conservation, and we called them the ghosts, okay? They were bad states which could ruin completely the theory. Then what I could call ghost hunting started. And what does that mean? Well, it means that fortunately, the full set of states that I presented in the previous transparency was redundant. It was sufficient to give factorization, but not necessary. Why? Because some linear combinations of those states were decoupled from any I and any F. Call them the spurious states, states which really decouple and which you can dispose of. Then the real question was, does one have a positive norm Hilbert space after the removal of the spurious states and not before? And in fact, some ghosts, those associated in fact with the first the time-like component of the first oscillator, were indeed found to be spurious by Sergio and myself. But that was hardly enough, because we had an infinity of such time-like creation operators, which were all producing negative norm states. At that point, Virasoro made a very important discovery. He found that for a very special value of alpha naught, one of those two parameters in the mass formula, in fact, for the value alpha naught equal 1, the number of spurious states increased dramatically. In fact, to put it in formulae, very simply, while Sergio and I found that a certain operator, which now is called L-1, acting on any state, and which contained the first harmonic oscillator, gave spurious states, Virasoro noticed that for alpha 0 equal 1, any L-n, an infinite set of such operators acting on any state was producing spurious states. So this was a very important generalization, which opened the way to the possibility, not the proof, but the possibility that ghosts could be completely eliminated, thus making the theory well-defined and consistent. Well, to prove the no-ghost theorem took a little while, and it was very important at this point to develop a formalism which would be as efficient, as elegant, as compact as possible. And this is the period I would like to call algebras, vertices, and fields. It started actually with a work by Liozzi, which is not often recalled, 69. He noticed that if you take that operator L-1 that created the Fourier states, the mass operator, redefined as L0, and the third operator, which also has some meaning, never mind, L+1, these three operators satisfy the Lie algebra of SO21, which is a non-compact version of ordinary three-dimensional rotations. In fact, I mean, if you, since at this time you may be a bit sleepy, I certainly am, you may think that this is the algebra of angular momentum, but of course this sign is wrong, and this sign is also wrong, okay, if you try to compare with the algebra of angular momentum. So Liozzi found this SO21 algebra underlying those operators. And then with Sergio, in a paper we published in a special volume of Annals of Physics dedicated to the late Amos de Chalit, whom I had, by the way, the great pleasure of meeting at the Weizmann Institute before coming here, we decided to try to take the full set of Virasoro operators L minus n, L0 again, and then some new operators L plus n, and try to generalize this result. And then we obtained should be quote unquote, the algebra. I mean, I'm still reading that paper and biting my fingers. We proposed that that was the correct generalization of that algebra to the Virasoro case. Okay? In fact, before the paper appeared in print, the late Joe Weiss, then I think at Berkeley, pointed out that we had made a stupid mistake, and that this algebra had an extra C number sitting on the right-hand side, a kind of Schwinger term, and that the correct algebra was this term plus a certain C over 12, n cubed minus n times the Kronecker delta n minus n. And that C turned out to be D, or the number of space-time dimensions in which we could consider the theory. Okay, so you see the crucial difference. And I mean, I think a posteriori this teaches me an important lesson. I mean, we couldn't guess anything else than this. This, of course, reproduces Liozzi's algebra correctly if n and m are 0, 1, or minus 1. But the stupid thing is that we could have done the explicit check, and we trusted so much our intuition not to do it, and this was obviously a big mistake. Anyway, this is, in fact, the famous algebra of the Virasoro operators, usually referred to as Virasoro algebra, but I want to point out that it was discovered, well, half at MIT and half at Berkeley. Now, the next thing was the following. In the work of Nambu and Fubini, Gordon, and myself, sorry, I didn't mention the names earlier, this is the work where the operators were introduced. The scattering amplitudes of the dual model were written as expectation values of product of vertices and propagators in analogy with field theory, all constructed out of these harmonic oscillators. But we know in field theory the harmonic oscillators come as the Fourier coefficients of the expansion of a field, phi of x. Now, as it has consistently happened in string theory and the dual model, you had to work backward. We had the operators, but we didn't have the field. So we had to work backward, but that was not too hard. And we with Sergio Fubini, we introduced an analogous field whose Fourier coefficients were precisely the harmonic oscillators that have been used. Well, that field had this funny appearance. Now, we didn't call it x mu, we called it q, but in any case, it had to do with some position. Now, sometimes position is called x, sometimes it's called q. In fact, the first piece is like a position operator of a normal particle. This p mu is nothing but the momentum operator of a normal particle. And this is the new piece. But we did not know what that new piece meant. Anyway, we had this field. Now, out of this field, one can construct the so-called vertex operators. And in terms of the vertex operators, finally, the scattering amplitude could be written simply as the expectation value of a product of these operators, precisely like in LSZ formalism, you write the scattering amplitude for n particles, you relate it to the expectation value of a product of local fields. So this formalism led to the possibility of studying further the theory and to its extensions, which I mentioned here. In particular, Di Vecchia del Giudice Fubini used it to construct physical states through which finally a proof of the no-gauss theorem came about by Richard Brouwer and independently by Goddard and Thorne. They proved that there were indeed no negative norm states in the theory, provided the number d of space-time dimensions was less or equal than 26. Let me jump here. In another development, loops, namely corrections to this narrow resonance approximation to give resonances a width, were constructed, and Lovelace was the first one to point out that actually the theory had to be in the equal 26. So the number of space-time dimensions in which these objects lived had to be quantized, if you want. And then the other extension, which is very important, is the one by Neveu, Schwartz, Ramond. They constructed a dual resonance model with both fermions and bosons, and you may know or may not know that that's where supersymmetry was first found, at least in the West, before it was applied to field theory. Okay, now, once you have a field, as I told you, so we went from the creation and destruction operators onto a field. Once you have the field, you can ask what is the field theory underlying the dual resonance model. Now, a posteriori, the answer is simple, but of course it took the genius of Nambu and also Goto to guess the right field theory. And the right field theory was the one of a relativistic string. In fact, inspired by the relativistic point, these people wrote an action for a massless relativistic string in a very simple form. The Nambu-Goto action, classical action for a string, is nothing but, I'm sorry this is a bit messed up, this doesn't belong to the formula, minus t times the integral over the area element, or if you want, times the total area swept by the string, which is this line, as it sweeps a surface during its motion. So you have to imagine this sheet embedded in capital D dimensional space-time, here represented by x1, x2, x3, but you have many more, as you see. And the action of Nambu and Goto was simply proportional to the area swept by the string. In more mathematical form, that area is related to the x mu that I was talking about by this formula, where alpha and beta are, can take values 1 and 2 and simply label the coordinates on this two-dimensional surface. Okay, never mind about the details. Now, this turned out to be a system with constraints. Namely, these d coordinates x mu of the string are not really all physical, in the sense that only the motion orthogonal to the string is physical. You see, a motion of the string which leaves this surface unchanged, a motion in the plane, in the surface, has no effect, and so it's unphysical. A posteriori, this is what eliminates some of the bad degrees of freedom which were giving us the problem. And in fact, the algebra of the classical constraints of the system was nothing but the algebra of the Virasoro operator that Fubini and I had, the one without C numbers. You see, again, this moving backward, okay? We had a quantum theory, and now, through this work, one is trying to reconstruct the classical theory of which what we had in our hands was the quantum version. And that is very interesting, because classically, the angular momentum and the mass of such a system is continuous, of course, and it turns out to satisfy a simple relation. The angular momentum of any string has to be bound by alpha prime times m squared, where alpha prime, just our old friend, the Regge slope, is related to this parameter t of the action by this inverse relationship. Now, however, things change drastically at the quantum level. At the quantum level, J, of course, is quantized, as everybody knows, and so is this mass squared. Less evident, but it is a fact. Now, in fact, you can impose now the validity of the constraints, not only of the classical constraint, over to the quantum level, and that was the fundamental work of Goddard, Goldstone, Rabi, and Thorne in '73, who found this way, through Lightbound quantization, that now at the quantum level, the correct results were that the angular momentum is less than alpha prime m squared plus alpha 0 h bar. Now, I put back h bar, which was 1 in most of the previous formulae. And then, of course, they found also that the algebra of the Virasoro operators had this extra central charge from the string point of view. And the consistency, namely imposing the constraint at the quantum level, required both alpha 0 equal 1 and the central charge to be 26. Therefore, required d equal 26. And this was, from the string point of view, but in perfect agreement with the Virasoro condition, alpha 0 equal 1, with loveless results about loops, with a no-ghost theorem and everything, okay? And, well, let me skip this for a second. With this work, we can say that the dual string theory had reached full maturity, okay? The circle was closed. But I also want to point out this very interesting conclusion, which, as you will see, is good and bad at the same time. And this is that states with zero mass and non-zero angular momentum, which are excluded for classical string because of that inequality, J less than m squared, are allowed, even necessary, at the quantum level. Okay? This is a very important point, which we'll see means the death of the old string and means life for the new one. In fact, what do I mean by this? That, you see, the string had reached complete maturity, was a perfectly elegant theory, but of course, as it should be the case, nature had its last word, has to have the last word on whether a theory is good or bad. And unfortunately, there were three basic properties of this beautiful, consistent theory, which represented as many death sentences for the old hadronic string. One are the massless states. As I say, at the quantum level, you get these massless states, spinning massless states. And we know, if there is one feature of strong interactions, we know for sure is this strong range nature. The excessive number of space-time dimensions. We were forced into that, again, by quantization, and it was an obvious problem. And third, less evident, is the momentum cutoff that there was at a GeV scale. Now, this last third property looked phenomenologically good at first. In fact, Hagedorn's model was based precisely on the idea that there was a cutoff, an exponential cutoff on high PT. But at least these three sets of experiments, the Slack experiments on deep inelastic collisions, on which we will hear tomorrow, the CEA experiment, E plus E minus 2 hadrons, showing a remarkably constant R. Finally, the ISR experiments at CERN on large angle hadron-hadron collision, large PT hadron-hadron collisions, they all reveal the presence of point-like constituents within the hadrons. And there were none in the string. So this third point was really pretty bad. And now at that time, QCD came about with quarks, gluons, with asymptotic freedom, which could justify the naive Parton model, could represent the data, and so on. And a dual string approach, though beautiful, consistent, and whatever you like, had to concede defeat. And sorry, I had to erase this. I was saying, see Roman Jakiv talk for the other side of the coin, but he talked about strings also instead of switch this subject. Now, well, the reason probably why I'm here is that this was really not the whole end of the story for strings. So I want to come to strings of the 90s, and so this means a jump of 20 years. And I will go quickly through those 20 years, but just by mentioning one point, that the bold proposal of Scherk and Schwartz in 1974. As I said, strings at the quantum level have inevitably massless spinning states. Now, such states do appear in nature, though not as hadrons. So their idea was, why not use strings for something else? Electromagnetic interactions, weak interactions, gravity, because other varieties of strings have massless particle of spin 2, for instance. And also, why not for strong interactions, but at the quark-gluon rather than at the hadron level. So, well, that proposal went quite unnoticed for some time. Meanwhile, the standard model got really established on firmer and firmer experimental grounds, as we know. But, okay, something which is often forgotten, it failed in one respect. It could not incorporate gravity. Okay, it's not yet a theory of quantum gravity. On the other hand, as John Schwartz puts it, quantum field theory clashes with gravity, and string theory can't even exist without it. And furthermore, seems to be a consistent theory of quantum gravity. Also, of course, there was the famous breakthrough of Green and Schwartz in 1984. And all this, plus this frustration about standard quantum field theory being unable to cope with quantum gravity, brought back strings in the front line. So in my last 5 minutes, I want to give you a little taste of how string theory has changed, has made its goals extremely bigger, but okay, we'll see that it won't be an easy job to check that. In fact, the 1990 version of the string action is slightly different from the one of Nambu and Goto, although one can prove some limits the equivalence of the two. It looks more like general relativity in 2 dimensions. And in fact, following the work of several groups, the new action, which is usually called the Polyakov action, due to the work of many groups, contains our old friend x of z, but also a new friend, a new person, a 2-dimensional metric. That's why I call it general relativity in 2 dimensions. This R, for instance, is just the Riemann curvature or the scalar curvature associated with this metric. And okay, these are the fields to be quantized. You'll see it's really a revolutionary point of view. Namely, you have to think of the position operator of the string and the two-dimensional metric as the quantum fields to be quantized or integrated over, if you like, more Feynman. By contrast, the fields which I underlined here, G mu nu, I use this capital G mu nu because it's conventional, phi, and others, are functions of x. This is not indicated, and are really like the ordinary space-time fields that quantum field theory usually deals with, and which quantum field theory, by definition, quantizes. Okay? Now, and then runs into problems when dealing with gravity, for instance. Now, the good news of this construction. Most of this is checked and true. I mean, maybe there is some slight wishful thinking, too. The good news is that the conditions of quantum consistency, namely the correct algebra of constraints, remember that those which gave us alpha 0 equal 1 and d equal 26, leads actually to equations of motions for the space-time fields, which are the usual classical field theory equations plus short-distance corrections. What does it mean? Einstein's equation for the gravitational field, or the Young-Mills equation, of the Maxwell equation, they come from the quantum consistency of that string action, okay, of that two-dimensional general relativity. It's very interesting. Classical field theory follows from the first quantization of the string, not from classical string, but from its quantization. Now, what about second quantization? You say that, I mean, the reason why we quantize usually the electromagnetic field, and we try also to quantize unsuccessfully the gravitational field, is because we want to have second quantization effect. Now, the remarkable thing about string theory is that there doesn't seem to be any need, and in fact it's probably wrong, to quantize G and phi the usual quantum field theory way, like imposing local commutation relations. In fact, the typical second quantization effects, like pair creation, running of coupling constant, what have you, follow simply from first quantization of the string, namely the same first quantization which gives the classical equations. If you carry that farther by being careful about how you integrate over the two-dimensional metric, I cannot explain the details, that reproduces also the second quantization effects. So it's very nice. You have a field theory in d dimensions, any d in principle, maybe with some limitation, and you can do all of that by quantizing a two-dimensional theory. Now, the usual ultraviolet divergences are tamed both in the gauge and in the gravity sector. This actually follows from the finite string size that strings acquire from quantization. Strings are like harmonic oscillators, and you certainly remember the delta x for the harmonic oscillator goes like the square root of h bar, of course, times the string tension. You get a fundamental length, okay? This was the cutoff which gave us trouble for hadronic strings vis-a-vis of, you know, the experiments. But certainly the cutoff is there, and now it's welcome instead of being, well, it's welcome because infinities in quantum field theory mean inconsistency if the theory is not renormalizable, or some lack of predictivity. For instance, renormalized parameters are arbitrary in field theory. Finiteness means predictivity, and in fact, strings can be shown to have really no free adjustable parameters. The parameters that enter in the theory are those which follow from the vacuum degeneracy. Okay. Now, in fact, there are two vacuum parameters in string theory which have dimensions of a speed and a length, and they are respectively the speed of light and this fundamental length, which turns out to be the Planck constant of the theory. There is this very interesting relationship in string theory between the Planck constant and the cutoff, which are completely unrelated in field theory. Furthermore, that field phi, which is called the dilaton, controls the fine structure constant and the Newton constant. And therefore, the two get related. And since they have different dimensions, they are related also through the fundamental length. And other scalar fields determine in principle the fate of extra dimensions, and through that, what is the gut scale and what is the symmetry there. Sorry, I'm very sketchy about these points, but it's just to give you a flavor of how much is at stake. Now, there are some bad news, and these are related to what Hermann was saying. A theory which cannot be wrong cannot be right. I think you said that, right? And this is this problem, that the relation between the gauge couplings and the Newton constant tell us that the new strings are not larger than, say, 10 times the Planck length. So there will be 10 to the minus 32 centimeters at. And then for most purposes, they look like points. And therefore, how can we shoot them down? How can we really see a distinction between strings and points? You see, the old hadronic strings were 10 to the minus 13 centimeters big, so they were giving effects at the GeV scale, and they could be ruled out simply on experimental grounds. And now I think this is a bit related to what Alan Guth was saying. When you talk about these scales, when you talk about these energies, probably there is only one hope, and this is cosmology, or using the universe as a whole as a way to test. And here is something a little bit in the same spirit. You see, the theory has massless scalars. What I mean by a hope, I mean a hope to be able to shoot down the string, okay? Or maybe prove that it's correct. Now, these are coupled to matter with typical gravitational strength. It's like a Brans-Dicke scalar, but with a small omega parameter, if you know what I mean. Their effect could contradict the basic tests of general relativity. Maybe they explain why Vicky Weisskopf feels heavier and heavier, but I'm sorry. Now, they are massless because of the flat directions, you see, which implied an arbitrariness in the vacuum expectation values and therefore in the fundamental constants of nature. I told you, there are no fundamental constants. The only one comes because the vacuum appears to be extremely degenerate in perturbation theory. So there is an undeterminacy on the value of some fundamental parameters. At the same time, as you know from the Goldstone theorem, there are massless particles which travel in this flat direction. These massless particles give trouble. So ultimately also this vacuum degeneracy is related to some symmetry which we start to understand. So it seems to me that the conclusion is that the new strings are also probably doomed unless some mechanism is found to break this huge symmetry which keeps the vacuum degenerate and therefore keeps these unwanted scalars massless and therefore also limits the predictivity of the theory. So perhaps fortunately the new string game may turn out to be an all-win or all-lose game, and I think that is how physics should be, and especially in the case of such a pretentious theory. Thank you.